Tonight, we're going to sit inside one of the most unsettling silences in the history of human thought. It started, of all places, at lunch. In the summer of 1950, at Los Alamos National Laboratory, a small group of physicists were walking to Fuller Lodge, trading jokes about a recent wave of UFO reports in the newspapers. The conversation drifted, as lunchtime conversations do, from one idle topic to the next. And then, seemingly out of nowhere, one of the men at the table, a physicist already famous for being able to estimate almost anything using nothing but the back of a napkin, blurted out a single question. The exact wording has been remembered slightly differently by each of the men who were there that day, but everyone agreed instantly on what he meant. Where is everybody? His name was Enrico Fermi, and the question he asked that afternoon, almost as a throwaway line between bites of lunch, has haunted physics, biology, and philosophy for 3/4 of a century. Here's what most people don't realize about that question. It isn't really a question about aliens, not in the shallow sense the word usually implies. It's a mathematical problem. Fermi did what Fermi always did. He ran the numbers silently in his head. Billions of stars, most of them far older than our own sun. A galaxy that could, in principle, be completely colonized in a matter of tens of millions of years. A blink of an eye compared to the galaxy's actual age. Given all of that, the math says the galaxy should already be full, loud, visible, practically shouting with evidence of other minds. Instead, nothing. 65 years of increasingly sophisticated listening, using instruments capable of detecting whispers across unimaginable distances, and not one single confirmed signal. Not one message. Not one structure. Not one mega project. Not one unambiguous trace of anyone else, anywhere, ever. The first surprise tonight is just how enormous, how overwhelming the case for a crowded galaxy actually is, and exactly how carefully and how completely that case has been tested against real observation. The second surprise is that there isn't one leading explanation for the silence. There are several, each one taken seriously by real scientists, and each one implying something completely different and completely consequential about what kind of universe we actually live in and what kind of future awaits us. The third surprise is that at least one of these explanations suggests something that should genuinely unsettle you, that finding even the simplest trace of alien life, a single microbe on a distant moon, might be one of the worst possible discoveries humanity could ever make. And the fourth surprise is that this isn't old news, safely resolved by some study you missed. This question is exactly as open right now, tonight, in 2026, as it was the day Fermi first asked it, and the newest, most powerful search in history is still listening, right now, and still hearing nothing. By the end of tonight, you're going to understand exactly why the universe is silent. Walk through every serious explanation scientists have proposed for that silence, and sit with what the answer, whichever one turns out to be true, actually means for us. Before we dive in, if you're someone who finds real comfort in sitting with the universe's biggest, quietest questions, who trades the noise of the day for a little cosmic perspective before sleep, consider liking this video or subscribing to the channel. It's a small thing, but it helps us keep making this kind of content for people who share that same quiet curiosity. Now, let's begin. Let's return to that walk to Fuller Lodge, because the context matters more than the punchline usually gets credit for. Enrico Fermi was already, by 1950, one of the most celebrated physicists alive, a man who had helped build the first nuclear reactor, who had won a Nobel Prize, and who had a particular reputation for something now called a Fermi problem, the ability to produce a startlingly accurate estimate for almost any enormous, seemingly unanswerable question using nothing but careful, patient, order of magnitude reasoning. How many piano tuners are there in Chicago? How many grains of sand are on a beach? Fermi could take a question like that, break it into smaller, more tractable pieces, and arrive at an answer close enough to correct that it seemed almost like magic. Walking to lunch that day with physicists Emil Konopinski, Edward Teller, and Herbert York, the conversation had been circling recent tabloid reports of flying saucers and, separately, a running joke about a series of local trash can thefts. Somewhere in the space between those two threads, Fermi went quiet. He was doing what he always did, running the numbers silently in his head. And then he asked it, "Where is everybody?" Konopinski, Teller, and York each remembered the exact phrasing slightly differently in later years. Some recalling it as, "But where is everybody?" Others as, "Don't you ever wonder where everybody is?" There is no verbatim transcript, but every single person at that table understood immediately, without any further explanation needed, that he wasn't asking about the missing trash cans. He meant the aliens. Fermi was not, in fact, the first person to formally raise this exact puzzle. In 1686, the French writer Bernard Le Bovier de Fontenelle wrote, in a popular book called Conversations on the Plurality of Worlds, that if the moon were genuinely inhabited, the moon's inhabitants would already have come to us. Jules Verne echoed a similar argument nearly 2 centuries later in his 1865 novel Around the Moon. And in the 1930s, the Soviet rocket pioneer Konstantin Tsiolkovsky formalized the reasoning further still, explicitly noting that the total absence of any visitors could itself be treated as evidence against the existence of advanced civilizations elsewhere. The idea had been quietly circulating, in one form or another, for 2.5 centuries before Fermi's lunchtime remark finally gave it a name that stuck. Now let's actually run Fermi's own back-of-the-napkin calculation together, because it's worth feeling the full weight of it. The Milky Way contains somewhere between 100 and 400 billion stars. Our own sun is 4.6 billion years old, but the galaxy itself is roughly 13.6 billion years old, meaning countless stars out there have had a genuine head start of up to 9 billion additional years to develop planets and life and, potentially, civilizations and technology and starships. Even at plausible, unglamorous, sublight interstellar travel speeds. Nothing exotic, nothing that violates any law of physics. A single civilization could, in principle, spread across and colonize the entire galaxy in something like 5 to 50 million years. That sounds enormous until you set it against the galaxy's actual age. 50 million years against 13.6 billion is genuinely brief. A geological eye blink. Here's a way to actually feel that timescale. If you compress the Milky Way's entire 13.6 billion year history down into a single human lifetime of 80 years, our own sun wouldn't have even formed until the final 27 years of that lifetime. And the entirety of recorded human history, every pyramid, every empire, every book ever written, would occupy just the last 0.02 of a second. Given that kind of head start available to countless other star systems, the mathematics doesn't just suggest the galaxy could be colonized. It suggests if even one civilization anywhere had done it at any point across that entire span, the whole galaxy should already, visibly, undeniably, be full. Picture walking into the largest library that has ever existed. 400 billion books, one for every star in our galaxy, expecting the low hum of countless readers turning pages, whispering, moving between the stacks. Instead, silence. Nothing but the quiet hum of the ventilation system and your own footsteps echoing down an endless, empty hall. This is the paradox in its full weight. Not a vague sense that we might be alone. A specific, numbers-driven expectation that we absolutely should not be, set directly against 65 years of the most careful listening our species has ever attempted. Before we walk through the possible explanations for the silence, it's worth understanding exactly how seriously and how thoroughly humanity has actually gone looking. The search formally began in 1960, when astronomer Frank Drake pointed the 26-meter Greenbank radio telescope, nestled in the hills of West Virginia, at two nearby sun-like stars, Tau Ceti and Epsilon Eridani. He called it Project Ozma, and he listened at a specific frequency, 1.420 gigahertz, the natural emission line of hydrogen, sometimes poetically called the water hole, because it's the frequency at which the two most fundamental ingredients of life, hydrogen and hydroxyl, both naturally resonate. It was, at the time, an almost audacious act of faith, pointing a single dish at two single stars for a matter of weeks, and genuinely wondering if anyone might answer. 13 years later, in 1973, Ohio State University switched on a radio telescope nicknamed Big Ear, beginning the world's first continuous, dedicated SETI program. And on August 15th, 1977, it recorded something that remains, to this day, the single most famous unexplained signal in the entire history of the search. A 72-second narrowband burst of radio energy at almost exactly 1,420.4 megahertz. The waterhole frequency, precisely where theory said an intentional signal would most likely be found. The astronomer reviewing the printout that later week was so startled by the signal's strength that he circled the data point in red pen and wrote a single word in the margin. Wow! It has never repeated. Not once. Not across more than 50 separate follow-up observations aimed at the exact same patch of sky in the decades since. Through the 1990s and early 2000s, the search continued to grow. Project Phoenix monitored roughly 1,000 nearby sun-like stars between 1995 and 2004. NASA briefly ran its own dedicated program, but it was cancelled after just a single year, following congressional funding cuts in 1993. SETI at Home, launched in 1999, distributed the analysis work across millions of ordinary home computers worldwide, and by 2010 had helped cover roughly 20% of the entire celestial sphere. And then, in January 2016, the search changed scale entirely. Breakthrough Listen launched with a 10-year commitment and a $100 million budget, the single most comprehensive SETI effort ever attempted by a wide margin. It targets a full 1 million nearby stars and 100 entire galaxies, scanning across a frequency range of 1 to 10 gigahertz, with active plans to extend that range further still, all the way up to 93 gigahertz. It covers 10 times more sky, 5 times more of the radio spectrum, and operates 100 times faster than every prior SETI survey combined. On any single day, Breakthrough Listen generates as much raw data as the entire history of SETI research produced in an entire year prior to its launch. In April and May of 2019, Breakthrough Listen's instruments caught something that briefly stopped everyone's breath. A narrowband signal at 982.002 MHz arriving from the exact direction of Proxima Centauri, our nearest stellar neighbour. It was formally disclosed to the public in December 2020, catalogued as BLC1, Breakthrough Listen Candidate 1. Careful follow-up analysis eventually concluded it was, almost certainly, ordinary terrestrial radio interference. A false alarm, dressed for one tense stretch of weeks in the clothing of something extraordinary. And more recently still, artificial intelligence pipelines developed at the SETI Institute have begun processing candidate signals roughly 600 times faster than previous manual and semi-automated methods allowed. An enormous leap in raw searching capability, arriving at almost exactly the moment this channel is speaking to you tonight. 65 years. From a single dish listening to 2 stars for a matter of weeks, to a globally coordinated, AI-assisted campaign scanning 1 million stars across 9 full gigahertz of bandwidth. And the confirmed technosignature count, after all of that effort, sits at exactly 0. Here's a way to hold the scale of that search honestly, though, because 0 doesn't mean nowhere left to look. Earth itself has only been leaking its own radio signals into space for about 100 years. A bubble roughly 100 light-years across, an almost laughably small patch relative to our galaxy's full 87, 400 light-year diameter. That bubble has, at most, washed over something like 1,000 nearby stars. Out of a galaxy containing perhaps 100 billion. That's a ratio of roughly 1 in 100 million. Astronomer Jill Tarter, one of the pioneering figures of the entire SETI field, has a standard way of describing exactly how incomplete our search remains, even after 65 years and Breakthrough Listen's staggering scale. It's like scooping a single glass of water out of Earth's oceans, finding no fish in that one glass, and concluding, with total confidence, that the oceans must be empty. We have listened, patiently and with genuinely extraordinary technology. And the honest, complete truth is that we have barely begun. In 1961, the same Frank Drake who had launched Project Ozma the year before organised the very first scientific conference ever dedicated entirely to the search for extraterrestrial intelligence. It was held at the Green Bank Observatory, and it drew exactly 10 scientists, among them a young astronomer named Carl Sagan. To help structure the conversation, Drake wrote a single equation on the meeting room's chalkboard, intended less as a rigorous scientific formula and more as an organised checklist, a way of breaking an impossibly large question down into smaller, individually more tractable pieces. The equation multiplies together 7 separate terms to estimate n, the number of currently communicating civilizations in our galaxy, the average rate of star formation, the fraction of those stars that have planets, the average number of habitable planets per star system, the fraction of those habitable planets that actually develop life, the fraction of life-bearing planets where that life develops intelligence, the fraction of intelligent species that go on to develop detectable communication technology, and finally, the average lifetime of a communicating civilization once it emerges. Using the values Drake and his colleagues estimated back in 1961, the equation produced an answer ranging from a minimum of 20 communicating civilizations in our galaxy, all the way up to a maximum of 50 million. A spread of 6 full orders of magnitude. That is not a small range. That is the entire equation in a single sentence, admitting just how little was actually known. More than 60 years of subsequent research have sharpened some of these terms considerably, while leaving others almost exactly as uncertain as they were the day Drake first wrote them down. The rate of star formation is now well measured at roughly 1.5 to 1.6 new stars per year across the galaxy. Microlensing surveys conducted in 2012 revealed that the fraction of stars hosting planets is likely close to 1, meaning, essentially, that nearly every single star in the galaxy has planets of some kind orbiting it. And a detailed 2020 analysis combining data from NASA's Kepler mission with the European Gaia satellite found that roughly half of all Sun-like stars host at least one rocky, potentially habitable planet in their star's habitable zone, implying a minimum of at least 300 million such worlds scattered across our galaxy alone. But the final 3 terms, the fraction of habitable planets that develop life at all, the fraction of that life that develops genuine intelligence, and the average lifespan of a communicating civilization once it emerges, remain almost entirely, genuinely unconstrained. We have exactly one confirmed data point for every single one of these terms, Earth. And extrapolating a universal probability from a single successful example is, scientifically, an extraordinarily fragile thing to do. In 2018, researchers Anders Sandberg, Eric Drexler, and Toby Ord took the Drake equation and did something the original version never really allowed for. They applied a rigorous, formal treatment of the uncertainty in each term, rather than simply multiplying single-point estimates together. Their conclusion was genuinely sobering. When you properly account for how enormous the uncertainty actually is in each individual factor, there turns out to be a substantial ex-ante probability, a real, mathematically meaningful chance that there is no other intelligent life anywhere in our entire observable universe at all. Not just our galaxy, the whole observable universe. the raw multiplication of confident single-number estimates, it turns out, quietly hides just how easily the entire product can collapse all the way down towards zero. A different team, astronomers Adam Frank and Woodruff Sullivan, approached the same underlying puzzle from the opposite direction in 2016. Rather than trying to estimate each term and multiply them together, they asked, given that no other technological civilization has ever been confirmed to exist anywhere, how astronomically unlikely would the emergence of intelligent life have to be on any single habitable planet for that total silence to actually make statistical sense? Their answer: the odds would need to be lower than roughly 1 in 10 to the 24th power per habitable planet. A genuinely, almost absurdly tiny threshold, suggesting that either intelligent life truly is staggeringly rare, or something else entirely is going on. Picture the Drake equation less as a precise scientific formula, and more as a recipe with 7 separate unknown ingredients. An attempt to bake a specific cake when you don't actually know the correct oven temperature, don't know exactly which ingredients you have on hand, and don't know how long the oven has even been running. Some of those unknowns, 65 years later, we've finally pinned down with real confidence. The most important ones, the ones that actually determine the final answer, remain almost exactly as wide open as they were the day Drake first chalked them onto that blackboard. Let's begin walking through the actual candidate explanations for the silence, the way a careful investigator would work through a genuine list of suspects. And the first, most straightforward explanation is also, in some ways, the most quietly devastating. Maybe there's no filter, no catastrophe, no hidden danger waiting somewhere in our future. Maybe the galaxy is simply, overwhelmingly, empty of anyone else. Not because something is stopping civilizations from arising, but because the specific, precise combination of conditions required to produce complex life in the first place is staggeringly, almost impossibly rare. This is the rare Earth hypothesis, popularized in a landmark 2000 book by paleontologist Peter Ward and astronomer Donald Brownlee. Their argument doesn't claim that simple life. Microbes, bacteria, the most basic chemical building blocks of biology, is rare at all. Quite the opposite. Simple microbial life, they argue, may genuinely be common, popping up wherever liquid water and basic chemistry allow. Their actual claim is considerably narrower and considerably stronger. That complex life, animals, plants, anything with a brain, anything capable of building a radio telescope, requires an almost implausibly precise stack of additional compounding conditions, layered one on top of another, any single one of which failing would leave a planet permanently, indefinitely stuck at the level of pond scum. The list of required conditions, as Ward and Brownlee lay it out, reads like an inventory of cosmic good fortune. A planet needs to sit within the galactic habitable zone. A specific ring, roughly 7 to 9 kiloparsecs from the galaxy's center, far enough out to avoid sterilizing radiation and the gravitational chaos of frequent near-miss supernovae, yet close enough in that the surrounding gas and dust actually contain enough heavy elements to build rocky planets at all. Researchers estimate this zone contains, at most, somewhere between 5 and 10% of all the stars in the Milky Way. It needs the right kind of star, long-lived and stable, not a violently flaring red dwarf. It needs a rocky planet of the right mass, sitting at the right distance from that star. Many versions of the hypothesis add a large guardian gas giant, positioned to gravitationally deflect incoming comets away from the inner solar system. A kind of celestial vacuum cleaner. Many versions add a large moon, stabilizing the planet's axial tilt and driving meaningful tides. The planet needs active plate tectonics and a strong magnetosphere, working together to recycle carbon and shield the surface from lethal radiation. It needs, over billions of years, a careful, delicate rhythm of evolutionary pressure. Ice ages and asteroid impacts severe enough to punctuate evolution and drive complexity forward, but never quite severe enough to sterilize the planet completely. And finally, It needs a series of genuinely rare biological breakthroughs along the way. The specific chemistry that first produced a eukaryotic cell, the emergence of sexual reproduction, the sudden explosive diversification of complex animal life during what's called the Cambrian explosion. Multiply all of these individual probabilities together, and Ward and Brownlee arrive at a combined estimate somewhere between 1 in 10 billion and 1 in a trillion. The rough odds, by their calculation, that any single habitable zone planet ever actually produces something as complex as an animal, let alone something as complex as a mind. Picture the entire chain of complex life as a Rube Goldberg machine, 4.5 billion years long, with dozens of separate, precisely calibrated marbles that all need to roll in exactly the right sequence, one after another, without a single misstep. Let just one marble take the wrong turn at any single point along that 4.5 billion year chain, and the entire cascade simply stops permanently at pond scum, with no way to restart the sequence and try again. It's genuinely important, in the spirit of honest investigation, to sit with exactly how contested nearly every single one of these individual rare Earth conditions actually is among working scientists. Because the hypothesis is considerably more fragile, evidentially, than its confident presentation sometimes suggests. Take the guardian gas giant. The intuitive logic feels solid. A large planet like Jupiter, sitting farther out in a solar system, should gravitationally sweep up or deflect incoming comets before they can reach the inner planets and cause a mass extinction. But planetary scientist James Casting has directly challenged this assumption, arguing that a large gas giant's gravity might actually be just as likely to fling comets inward toward the habitable zone as it is to protect against them. Meaning Jupiter's true net effect on Earth's habitability over billions of years remains genuinely, scientifically unresolved. Take the large stabilizing moon. The standard argument holds that without our unusually large moon, Earth's axial tilt would wobble chaotically over millions of years, producing climate swings too severe for complex life to reliably survive. But Casting has pushed back here too, arguing that even a moonless Earth would likely remain genuinely habitable. The wobble, while real, may simply not be as catastrophic as the rare Earth argument assumes. Take plate tectonics itself, often treated as an absolute, non-negotiable requirement for long-term habitability, since it recycles carbon dioxide and helps regulate a planet's climate over geological time. More recent research into so-called stagnant lid tectonics, a very different geological regime without Earth's mobile, subducting plates, suggests that even planets without conventional plate tectonics might still be capable of supporting life through alternative, less well-understood mechanisms. And there's a deeper, more structural problem sitting underneath all of these individual disputes. Ward and Brownlee's final combined estimate, that 1 in 10 billion to 1 in a trillion figure, is built entirely from stacking together a series of individual point estimates multiplied against one another. But almost none of those individual point estimates rest on any genuine, independent empirical measurement. They are, for the most part, informed guesses, layered on top of other informed guesses, compounding uncertainty at every single step of the multiplication. None of this means rare Earth is wrong. It may well be substantially correct. Genuinely, our own planet's specific history might represent an extraordinarily unusual, fortunate sequence of events. But the honest scientific position is that we currently have no reliable way to actually verify most of the individual factors the hypothesis depends on. Being dealt a royal flush 9 separate hands in a row across a 4.5 billion year game clock is an evocative image for just how unlikely complex life might genuinely be. It is also, right now, an image built substantially on inference and plausible reasoning, rather than hard, independently verified data. Here's a second explanation, and it carries a considerably gentler, more hopeful shape than the first. Maybe the galaxy genuinely is full of other civilizations. Maybe we simply haven't built the right tools, pointed them in the right direction, at the right time, in the right way, to actually notice them yet. The case for this explanation begins with a simple, honest accounting of exactly how limited our own search capability genuinely remains, even after 65 years of dedicated effort. Earth's own radio leakage. The accumulated broadcast signals from a century of television, radio, and radar, drifting outward into space at the speed of light, currently forms a bubble roughly 100 light-years across. Against our galaxy's full 87 400 light-year diameter, that bubble is a rounding error. It has, at most, washed past perhaps 1,000 nearby star systems, out of a galaxy containing something like 100 billion. If any other civilization out there is listening for exactly the kind of leakage signal we ourselves produce, the overwhelming majority of the galaxy has never once received so much as a whisper from Earth. And the reverse problem is just as severe. Voyager 1, the fastest and most distant human-made object ever launched, travels at approximately 17 kilometers per second, roughly 3.6 astronomical units every year. At that speed, reaching even our very nearest stellar neighbour, Proxima Centauri, just 4.24 light-years away, would take somewhere between 73,000 and 77,000 years. Here's a way to feel that number directly. If Voyager 1 were instead a person, walking at an ordinary, unhurried pace of 5 kilometers per hour, the same journey to Proxima Centauri would take roughly 900 million years, considerably longer than the entire existence of our species by a factor of thousands. Detecting a signal of ordinary, Earth-like broadcast strength from another star system would require a receiving instrument with an effective collecting area on the order of 1 million square meters, comparable to the largest radio arrays currently being built or planned, like the Square Kilometre Array or China's FAST telescope. FAST, in principle, could scan roughly 1 million target stars for a signal, but only if that hypothetical transmitter were broadcasting at a power output of 1 million megawatts, a figure orders of magnitude beyond anything any human transmitter has ever produced. And even setting aside raw sensitivity, the sheer size of the search space remains genuinely staggering. SETI's efforts have concentrated overwhelmingly on the 1 to 10 GHz radio band, a comparatively narrow slice of the full electromagnetic spectrum. Optical signals, infrared communication, and more speculative channels like tightly focused laser pulses remain almost entirely unexplored. Multiply the search space across every dimension simultaneously. Which direction in the sky, which exact frequency, which modulation scheme, which precise moment in time a signal might arrive, and how powerful any given transmitter might actually be. And even Breakthrough Listen, the most comprehensive search ever conducted, has covered barely a fraction of a percent of the full theoretical parameter, space. This is precisely the logic behind Jill Tarter's glass of ocean water analogy, and it's worth returning to directly. We have scooped up one glass. We found no fish in it. Declaring the entire ocean lifeless, on that basis alone, would be a genuinely unjustifiable conclusion. And yet it's uncomfortably close to what casual dismissals of the silence often, implicitly, assume. Picture standing on a beach at midnight, straining to spot a single firefly somewhere on the far, invisible shore of an entire ocean. The absence of a visible flicker doesn't mean the far shore is empty. It might simply mean you're looking across too much darkness, with too narrow a field of view, for too short a time, in only one of the countless directions a firefly might actually be glowing. Here's where the investigation turns genuinely unsettling, because this next explanation doesn't simply suggest we haven't looked hard enough, or that life is merely rare. It suggests something is actively, systematically stopping civilizations from ever reaching the stage where they'd be loud enough to notice. And it doesn't tell us whether that obstacle lies safely behind us or still waits somewhere ahead. The idea was formally proposed in 1998 by economist Robin Hanson in an essay titled, with genuine bluntness, The Great Filter. Are we almost past it? His central logic runs like this. Among the roughly 10 to the 22nd power stars we can observe across the visible universe, not one has ever produced a confirmed, visible, galaxy-spanning civilization. Given how enormous that number of stars actually is, and given how much time has been available for such a civilization to arise, at least one single step along the chain, from lifeless matter all the way up to an expanding, lasting, technological civilization, must be extraordinarily, almost impossibly improbable. That one improbable step is what Hansen named the Great Filter. He laid out 9 candidate stages where that filter might be hiding. The formation of the right kind of star system in the first place, the emergence of the first reproductive molecules like RNA, the appearance of simple, single-celled prokaryotic life, the much later emergence of complex, single-celled eukaryotic life, the evolution of sexual reproduction, the rise of genuine multicellular organisms, the eventual development of tool-using intelligence, a civilization approaching the technological threshold of a colonization explosion, and finally, the colonization explosion itself, the actual physical spread of a civilization outward into its galaxy. Here is the dilemma that makes this explanation so genuinely difficult to sit with. If the Great Filter sits behind us, if, say, the improbable leap was the original emergence of complex eukaryotic cells, a genuine 1 in a billion biochemical accident, then Earth has already won an extraordinary cosmic lottery, and humanity's own future might, in principle, remain wide open and hopeful. We would already have cleared the hardest part. But if the filter sits ahead of us, if the truly improbable step is something we haven't yet reached, something like a civilization successfully surviving its own advancing technology without self-destructing, or successfully making the leap to genuine interstellar expansion, then no civilization anywhere has ever crossed it, which would mean, quite plainly, that we probably won't either. And here is Hansen's single most disturbing implication, the one that genuinely reframes the entire search for extraterrestrial life. If we were to discover even the simplest form of independently arisen life somewhere else in our own solar system, a genuine microbe found on Mars or in the subsurface ocean of a moon like Europa, confirmed to have evolved completely independently of life on Earth, that discovery would tell us that the early biological steps from simple chemistry through to basic single-celled life are relatively easy hurdles to clear, which would mean the true, remaining improbable step has to be pushed forward later in the chain. Closer to us, closer to our own present moment, closer to our own future. In this specific, careful framing, finding alien life would be worse news than finding nothing at all. Picture a long corridor, lined with doors on either side. Behind some of those doors, the ones you've already walked through, sits a specific set of odds you've already, unknowingly, beaten. Ahead of you, somewhere further down that same corridor, one more door might be locked from the outside entirely, impossible to open no matter how advanced you become. You don't know, standing where you're standing right now, which kind of door you're actually approaching next. There's a fourth explanation, and it doesn't suggest life is rare, or that some cosmic accident is blocking civilizations from emerging. It suggests something considerably colder, that the galaxy is full of other minds, and every single one of them has made the exact same, entirely rational decision to stay absolutely, deliberately silent. The idea was popularized by the Chinese science fiction author Liu Cixin in his 2008 novel The Dark Forest, the second book in his celebrated Remembrance of Earth's Past trilogy. A related, earlier scientific version of essentially the same reasoning had already been proposed decades before, in 1983, by astronomer David Brin in a formal academic review of the Fermi Paradox, under the framing of what he called a deadly probes scenario. The logic can be modelled with genuine mathematical precision as a game theory problem. Specifically, a sequential game played under conditions of incomplete information, where the only real win condition is survival, and where vital resources across the universe are assumed to be finite. Under this framing, every civilization that ever detects evidence of another has, functionally, exactly 3 possible moves available to it: destroy the other civilization preemptively, broadcast openly, and risk being destroyed in turn, or simply, permanently, stay silent. Liu Cixin builds this into 3 foundational axioms of what he calls cosmic sociology. First, many civilizations exist, scattered across the universe. Second, survival is the primary, overriding need of every single one of them. Third, civilizations naturally tend to expand outward over time, while the total matter and resources available to expand into remain fundamentally finite. From those 3 simple premises, the dark forest reasoning builds toward its conclusion through 3 specific ingredients. First, the uncertainty of intent. Across light years of distance and potentially thousands of years of communication delay, you can never actually verify whether another civilization's true intentions are peaceful or hostile. Second, the chain of suspicion. Even if you yourself are entirely benevolent, you have absolutely no way of confirming that the civilization you've just detected reasons the same way. Which means, from their perspective, preemptively striking you might appear to be the only rational choice available to them, and knowing that, it might become rational for you to strike first instead. And third, the technological explosion problem. A civilization that appears to be far behind you today, technologically, might leap dramatically ahead of you by the time any reply you send actually arrives, decades or centuries later. Meaning any civilization you encounter as a rough equal today could, by the time you've finished exchanging messages, have quietly become your annihilator instead. The conclusion the logic drives toward is bleak and specific. Broadcast your presence to the universe, and sooner or later, someone, somewhere, will silence you for it. The only genuinely safe strategy is to stay dark. This isn't purely academic speculation, either. It intersects directly with a genuine, ongoing, real-world scientific controversy over something called METI. Messaging extraterrestrial intelligence, the deliberate practice of intentionally beaming powerful signals toward other star systems, rather than simply listening passively. Astronomer and science fiction writer David Brin, alongside physicist Stephen Hawking, has publicly, repeatedly warned against this practice, precisely on dark forest-style grounds. Others, including Douglas Vakosh of the organization METI International, argue the actual risk is close to negligible, since Earth's own accidental radio leakage has already been broadcasting outward, continuously, for over a century regardless of any deliberate choice, meaning the genie, in a meaningful sense, is already out of the bottle. The dark forest hypothesis does have serious critics, and it's worth including their reasoning honestly. Economist Robin Hanson himself, along with writer Noah Smith and others, has argued that the actual payoff structure required to make the dark forest strategy genuinely stable simply doesn't hold up under closer mathematical scrutiny. The cost of mounting an actual interstellar attack against a distant civilization would be enormous, requiring resources and coordination on a scale that dwarfs almost any plausible benefit. The potential gain from such an attack would likely be modest, and crucially, an attacking civilization could never actually verify, in real time, whether its attack had genuinely succeeded, given the light lag involved. Taken together, these critics argue the entire strategic logic may simply be less rational and less stable than the compelling fictional framing makes it feel. Liu's own central image remains the clearest way to hold the idea in mind, regardless of which side of the debate you find more persuasive. A lone hunter, standing in a pitch-black forest, rifle raised, listening. Every rustle in the underbrush could be prey. It could just as easily be a predator. You do not call out to try to find friends. You simply, quietly wait. Here's a fifth explanation. And unlike the dark forest's cold, external logic, this one turns the danger entirely inward. This was, in fact, one of the very earliest interpretations offered for Drake's final equation term. L, the average lifespan of a communicating civilization once it emerges. Carl Sagan himself, along with several of his contemporaries, argued as early as the 1960s and continuing through the 1980s that L might simply be short, not because of any external threat, but because civilizations reliably, almost inevitably, invent the very tools capable of ending themselves. At roughly the same moment, they become advanced enough to broadcast their presence to the stars. More recent, formal academic treatments have deepened this reasoning considerably. Researcher Nathan Alexander Sears, writing in 2020, formalized what he calls the anarchy technology dilemma. As any civilization's technological capability continues to grow, so too does its capacity for genuinely catastrophic, self-inflicted destruction. While the political coordination required to safely manage that growing capability tends, structurally, to lag significantly behind it. Separately, astronomer Adam Frank and his colleagues, publishing in 2018 and again in 2021, built detailed mathematical models treating a civilization and its host planet as a single, tightly coupled system, evolving together over time. Their models found that energy-harvesting civilizations reliably drive their own planets through something resembling an Anthropocene-style tipping point, a genuinely difficult planetary transition that most of their simulated trajectories struggled to survive, with only a narrow band of outcomes leading toward long-term sustainability rather than collapse or forced retreat. Frank has since described this pattern as a possible soft great filter, not a single, sudden catastrophic event, but a genuine test, built directly into the physics and thermodynamics of what it actually means to become a technological civilization powerful enough to reshape your own planet. Candidate pathways for this kind of self-destruction span a genuinely wide range: nuclear war, engineered pandemics, runaway climate change, uncontrolled advanced artificial intelligence, broader ecosystem collapse. Every single one of these remains, honestly, highly speculative as a universal, galaxy-wide mechanism. There's a real case both for and against taking this explanation seriously, and intellectual honesty requires sitting with both sides, in its favor. Humanity itself is currently the only confirmed technological civilization we know of, and we invented planetary-scale destructive capability, nuclear weapons chief among them, within roughly 150 years of beginning industrialization. That's an extraordinarily narrow window on any cosmic timescale between harnessing fire and steam and possessing the technical means to end organized civilization. Against it, we have exactly one data point, us, and we have not, so far, actually destroyed ourselves. Drawing a confident, universal conclusion from a sample size of exactly one civilization is scientifically fragile, almost by definition. Sagan's own original numerical framing is worth holding on to directly. If L, the average communicating lifespan of a civilization, turns out to be measured only in decades or centuries rather than millennia or longer, then even across a galaxy that has produced hundreds of billions of stars over its full 13.6 billion year history, the number of civilizations simultaneously broadcasting at any single given moment would be small, vanishingly small, and the odds of any one of them happening to fall within our own narrow detection radius during our own narrow window of listening would drop correspondingly, dramatically low. Picture a civilization that has just discovered planetary-scale weapons the way a toddler picks up a lit match, standing inside a house built entirely of dry wood. There are, genuinely, a great many ways that particular story can end badly. And here's the timescale worth sitting with. Even if a civilization's full technological era somehow lasted 10,000 years, twice the entire span of recorded human history, that would still represent only about 700 thousandths of 1% of the galaxy's total age. A single heartbeat in an otherwise very, very long life. We've now walked through 5 genuinely serious candidate explanations for the silence, the way a careful investigator works through a full list of suspects, one at a time. Rare earth, undetectability, the great filter, the dark forest, self-destruction. Each one is taken seriously by real, credentialed researchers. Each one is built on genuine evidence and genuine reasoning. And here is the honest verdict. Once all 5 have been given a fair hearing, none of them has been proven. And critically, none of them actually rules out any of the others. This isn't a failure of the investigation. It's simply the nature of the evidence available. Astrophysicist and science writer Stephen Webb, in his book, If the Universe is Teeming with Aliens, Where is Everybody?, catalogued a full 75 distinct proposed solutions to the Fermi Paradox in the book's 2nd edition alone, of which the 5 we've covered tonight represent only the most prominent, most rigorously developed cluster. The 5 explanations we've walked through can all be partially true simultaneously, layered on top of one another, each one contributing some fraction of the total explanation for the silence, rather than any single one standing alone as the complete answer. And here's what makes this particular investigation genuinely different from an ordinary mystery. Each possible verdict implies a completely different future for our own species, not just an answer to an abstract puzzle about the past. If rare earth is substantially correct, then Earth is something close to a museum piece. Complex life might be nearly, genuinely ours alone within our entire galaxy, a staggeringly improbable accident that will likely never repeat nearby. If the undetectability explanation is closer to correct, then other civilizations are out there right now, waiting quietly to be found. And the honest answer to Fermi's question is simply that we need more time, more dishes, more spectrum, and more patience. If the great filter sits safely behind us, we are extraordinarily lucky, having already cleared the hardest, most improbable step, with a genuinely open future ahead. If the great filter still waits somewhere ahead of us, then the specific challenges of our own century, nuclear weapons, climate change, advanced artificial intelligence, may be the exact test that determines whether our own voice ever crosses interstellar distance at all, or falls permanently silent like everyone else's apparently has. If the dark forest reasoning holds, then silence itself may be a form of hard-won wisdom, one we may eventually need to learn and adopt ourselves. And if civilizations simply, reliably self-destruct, then whatever choices we make to survive the next few centuries are themselves the answer that will, one way or another, echo outward, or not, into the silence that follows us. Whichever explanation, or combination of explanations, eventually turns out to be true, one fact remains completely unchanged in the meantime. Right now, tonight, humanity is the only confirmed voice we can point to anywhere in the observable universe. And that fact, regardless of why the rest of the galaxy stays silent, carries its own particular kind of weight. Given how much genuine uncertainty surrounds every explanation we've covered tonight, it's worth asking a more practical, grounded question. If a real signal or a real trace of alien biology actually arrived tomorrow, how would scientists even know? What would it actually take to be believed? In October 2021, a team led by James Green, then NASA's chief scientist, published a formal framework in the journal Nature, designed to answer exactly this question. It's called the Confidence of Life Detection Scale, CoLD for short, and it lays out 7 progressive, deliberately demanding levels of confirmation that any potential biosignature has to climb through before the scientific community will treat it as genuine evidence of life. First, detect a possible signal at all. Second, rule out any possibility of contamination from Earth itself. Third, confirm that the environment in question could plausibly support biology in the first place. Fourth, systematically rule out every plausible non-biological explanation for the signal. Fifth, find a completely independent, second signal that corroborates the first. Sixth, rule out alternative explanations for that second signal too. And only at the 7th and final level, achieve genuine, independent confirmation from separate research teams using separate methods. This isn't excessive caution for its own sake. It's the direct, hard-won product of an entire field that has been burned, repeatedly, by premature excitement. Which brings us to some of the most genuinely dramatic false alarms in the entire history of the search. The current live example sits on the surface of Mars right now. In July 2024, NASA's Perseverance rover, exploring a channel called Neretva Vallis, drove over and cracked open a rock later nicknamed Chayava Falls, revealing organic carbon-bearing mudstone dotted with distinctive sub-millimeter mineral spots. In September 2025, the mission's science team formally classified this discovery as a potential biosignature, but only at the very lowest levels of the CoLD scale, level 1 or 2. Confirming it any further will require physically returning that exact sample to Earth for full laboratory analysis, a mission that remains, as of this telling, genuinely uncertain in its funding and timeline. Think of the CoLD scale as functioning something like a criminal trial, where the prosecution. In this case, the hypothesis that we've genuinely found life bears the full burden of first eliminating every single plausible innocent explanation before biology is even seriously entertained as the answer. Biology, in this framework, is treated as the verdict of last resort, arrived at only once every other, more mundane explanation has been carefully, systematically ruled out. The history of this exact standard being tested, and again, holding firm, is genuinely one of the richest, most human parts of this entire story. On November 28, 1967, a young PhD student at Cambridge named Jocelyn Bell Burnell detected something in her radio telescope data that made no immediate sense, a signal pulsing with impossibly precise regularity, once every 1.3373 seconds, each pulse lasting just 0.04 of a second, arriving from the direction of the constellation Vulpecula. The regularity was so exact, so mechanically precise, that Bell Burnell and her supervisor half-jokingly labelled the source LGM1, Little Green Men. For a genuinely tense stretch of weeks, an artificial, intelligently generated signal remained a real, seriously considered possibility. The alien explanation was ultimately ruled out when a second, nearly identical pulsing source was discovered elsewhere in the sky. Proof that this was a natural phenomenon after all, and in the process, the entire discovery of pulsars, rapidly rotating neutron stars, was born. Then there's the wow signal itself, which we touched on earlier. That 72-second, extraordinarily strong burst recorded by Ohio State's Big Ear in 1977, at almost exactly the frequency theory predicted an intentional signal would use, and never once repeated across more than 50 subsequent attempts to find it again. A 2024 preprint from the Planetary Habitability Laboratory proposed a specific natural explanation. A rare astrophysical event in which stellar emission briefly energizes a cold cloud of hydrogen gas into a sudden brightness surge. It remains, honestly, a proposal rather than a settled scientific consensus. Nearly 50 years later, the wow signal remains astronomy's own version of a Bigfoot photograph, famous, genuinely tantalizing, and permanently missing its second frame. On October 19th, 2017, astronomers detected the first confirmed interstellar object ever to pass directly through our solar system, an object given the name Oumuamua, arriving on a sharply hyperbolic trajectory from the direction of the star Vega. It was unusually elongated, somewhere between 101,000 meters long, and displayed a genuinely puzzling non-gravitational acceleration as it departed. Speeding up slightly, in a way gravity alone couldn't explain, without showing any of the visible gas or dust tail that normally accompanies that kind of outgassing-driven acceleration in a comet. In 2018, Harvard astronomer Avi Loeb, along with colleague Shmuel Bialy, proposed a genuinely startling alternative explanation, that Oumuamua might be an artificial object entirely, perhaps a thin, artificial solar sail. The mainstream scientific consensus, solidifying by 2019 and reinforced again in 2023, is that Oumuamua is very likely a natural interstellar comet fragment, its unusual acceleration most plausibly explained by outgassing of molecular hydrogen trapped within water ice. Though even among researchers who reject Loeb's artificial origin hypothesis, the precise natural mechanism involved remains an area of genuine, ongoing scientific discussion. And then there's Venus. On September 14th, 2020, a research team led by astronomer Jane Greaves reported detecting phosphine gas in the planet's thick cloud decks at a concentration of roughly 20 parts per billion, using observations from 2 separate radio telescope facilities. The reason this mattered so much: no known non-biological chemical process on a hot, hostile, rocky world like Venus should be capable of producing phosphine at that particular abundance, which meant biology had to be seriously floated as one genuinely possible explanation. What followed was a rapid, intense wave of scientific reanalysis. Multiple separate teams argued the original signal was a statistical artifact, or had been misidentified as sulfur dioxide instead, or actually sat below any reliable detection threshold in the first place. As of the most recent work in 2024, Greaves' own research team has reasserted a fresh detection using new observations, and separate infrared studies offer some additional supporting evidence. But the underlying dispute genuinely, actively remains unresolved. No confirmed abiotic mechanism has yet fully explained the reported abundance, and biology remains, honestly, a minority interpretation rather than the leading one. Each one of these episodes, the pulsar, the wow signal, Oumuamua, Venusian phosphine, followed an almost identical emotional arc, a genuinely startling initial signal, a wave of serious, careful scientific excitement, and then months or years of increasingly rigorous scrutiny, driving the field's evidentiary standards higher and higher with every single case. This is precisely why the CoLD scale demands 7 separate levels of confirmation before treating any signal as genuine evidence of life. Extraordinary claims, tested against this specific history of near misses, have consistently and repeatedly required extraordinary, patient, multi-year evidence before the scientific community will actually accept them. Before we close, let's gather everything we've walked through tonight, all together, and actually sit with the true scale of it. The observable universe contains somewhere between 10 to the 22nd and 10 to the 24th power stars. More, by any reasonable count, than every single grain of sand on every beach on planet Earth combined. Carl Sagan himself once put it with characteristic elegance: there are more stars in the universe than there have been seconds since Earth itself formed. More stars than every word ever spoken by every human being who has ever lived. Our own galaxy is itself in motion, orbiting the distant center of the Milky Way at roughly 230 kilometers per second, 828,000 kilometers per hour. A single complete orbit, astronomers call a galactic year, takes approximately 230 million Earth years to complete. Our own Sun, in its entire 4.6 billion year existence, has completed roughly 20 of these galactic years since it first formed. And against that entire staggering scale, trillions of stars, hundreds of galactic years, 65 years of increasingly sophisticated listening, the confirmed number of other voices we have ever detected, anywhere, remains exactly 0. Every one of the 5 explanations we've walked through tonight offers its own answer for why, but none of them has been proven. Each remains, honestly, a proposal rather than a settled conclusion. One candidate solution among the 75 that Stephen Webb catalogued, each one internally consistent, each one built on genuine reasoning, and none of them yet confirmed by direct evidence. Picture the entire universe as a cathedral so vast that it swallows sound entirely. A space with enough silent, echoing volume that even a shout, somewhere far enough away, simply never arrives. You sit in your own small pew, in your own small corner of that cathedral, and listen carefully for the faint sound of another cough, somewhere in the darkness beyond your own hearing. you haven't heard one yet. That silence doesn't tell you, with any certainty, whether the rest of the cathedral is genuinely empty or simply too vast, too dark, and too far away for any sound to have reached you yet. There's something worth sitting with directly, now that we've walked through this entire investigation together. Fermi's original question, "Where is everybody?" was never really answered tonight. It couldn't be. No one currently has that answer. What we found instead, walking carefully through each candidate explanation, was something considerably more interesting than a tidy resolution. A set of genuinely different mirrors, each one reflecting a different possible truth about our own place in the universe and about our own likely future. If we are simply rare, if rare Earth captures something fundamentally true about how difficult complex life genuinely is to produce, then Earth is not a typical outcome of typical cosmic processes. It's something closer to a miracle, in the most literal, statistical sense of that word. An outcome so improbable that its actual occurrence demands real wonder, rather than casual assumption. If the silence is simply a matter of technological limitation, if other minds are genuinely out there, patiently waiting to be found, just beyond the current reach of our instruments, then the responsibility resting on us is different in character. It becomes a responsibility to keep listening, to keep building better dishes, wider bandwidths, smarter algorithms, to not give up on a search that has, so far, taken 65 years and found nothing, precisely because nothing found yet and nothing there have never been the same statement. If a filter waits somewhere ahead of us in the chain of great filter stages, if the truly difficult step in becoming a lasting, communicating civilization is still something our own species hasn't yet cleared, then the specific choices we make across the next 100 or 200 years may quietly determine whether human civilization ever becomes one of the rare few to actually cross that threshold, or simply joins the vast, silent majority that apparently never has. And if the deepest truth is something closer to the dark forest, or to civilizations simply reliably destroying themselves, then perhaps the most useful lesson available to us isn't really about aliens at all. It's about what any civilization, anywhere, eventually has to learn about restraint, about coexistence, about surviving its own most dangerous capabilities long enough to have a future worth broadcasting about in the first place. We don't currently know which of these mirrors reflects the actual truth. Quite possibly, elements of several of them are simultaneously, partially correct. What we do know with genuine certainty is this. Right now, in this exact moment, humanity is the only confirmed voice anywhere in the observable universe. Whatever else that fact turns out to mean, it is not a small thing to be. Picture it one last time before we close tonight. Somewhere above you, right now, roughly 200 to 400 billion stars are quietly burning inside our own galaxy alone. Each one a candle in that vast, silent library we described at the very beginning of tonight's investigation. Somewhere among them, perhaps, other minds are doing exactly what you are doing right now, lying in the dark, listening, wondering whether anyone else is out there wondering the same thing. Or perhaps not. Perhaps the library truly is as empty as it currently sounds. Every one of those hundreds of billions of candles burning in genuine, permanent solitude, with no reader ever destined to walk past them at all. We don't know which. 65 years of the most careful listening our species has ever managed hasn't told us. Every serious explanation we've walked through tonight remains, honestly, a proposal rather than a proof. And that not knowing, rather than being something to fear, might be one of the more remarkable facts about the specific moment in history we happen to occupy. We are the generation, out of every generation that has ever lived, actually equipped with the instruments, the mathematics, and the patience to keep asking the question seriously, rather than simply wondering about it around a fire. Imagine the entire observable universe reduced to a single, still lake, glimpsed at first light, just before dawn. Somewhere on that vast, quiet surface, one ripple spreads outward. Small, recent, easily overlooked against the enormous stillness surrounding it. That ripple is us. Whether other ripples exist somewhere beyond the horizon of what we can currently see, whether they were always out there, simply too distant to notice yet, or whether the lake genuinely, truly is this still everywhere else, is the exact question that keeps the water quiet tonight. We are the first ripple we know of, and we are, for now, still spreading. Tonight we sat with one of the deepest silences in the history of human thought. Enrico Fermi's simple lunchtime question and the 65 years of increasingly sophisticated listening that have followed it. We found a galaxy that, by the raw mathematics of stars and time and colonization speed, should already be loud with the evidence of other civilizations. Set directly against a search history that has grown from a single dish listening to 2 stars, to a globally coordinated, AI-assisted campaign scanning 1 million stars across 9 gigahertz of bandwidth, and has found, after all of that effort, exactly nothing confirmed. We found 5 serious, carefully reasoned candidate explanations for that silence. That we are simply rare, that others are out there but undetectable with our current tools, that some great filter sits behind us or ahead of us, that a dark forest logic keeps every civilization deliberately silent, and that civilizations may simply, reliably destroy themselves before they can be heard. And we found that none of them has been proven, and that several of them may well be true simultaneously. We found a scientific standard, the CoLD scale, built directly from a history of genuine near misses. A pulsar mistaken for little green men, a signal that said, "Wow!" and never repeated, an interstellar visitor that might have been a sail, a planet that might, or might not, be breathing phosphine into its own clouds. Each one teaching the field to demand more evidence, not less, before ever declaring the silence broken. And we found, underneath all of it, a single, quiet, undeniable fact. Right now, tonight, humanity remains the only confirmed voice anywhere in the observable universe. Whether that's because we are rare, or early, or lucky, or simply still listening in the wrong place, remains genuinely, honestly unknown. Fermi's question was never really about aliens, not entirely. It was always, in some sense, a question about us, about what kind of civilization we are, and what kind of civilization we might yet become. Standing here, listening, in a universe that has not yet answered back. Sleep well tonight, knowing that somewhere above you, in the vast, quiet dark, the search continues. Patiently, carefully, without pause, for the second voice that would finally tell us we were never entirely alone. Good night, and rest well under a sky that is, for now, still listening back in silence.